All right, welcome to The Explainer. Today we're jumping into something really cool, computational materials science. We're going to see how scientists are literally designing the materials of the future, one single atom at a time.
So, let's get right into it. Our story actually starts not in some pristine lab, but with a pretty dramatic, high-stakes failure. We're talking about a jet engine turbine blade.
Now you have to understand, these parts, things like the nickel-based superalloys that companies like Rolls-Royce use, they are engineered to handle just insane amounts of heat and stress. I mean, they're the best of the best. So the big question is, what went wrong? How does something that strong just break?
Well, for the longest time, the way we made new materials was honestly kind of primitive. It was all physical trial and error. You'd literally mix some elements together, heat them up, make a part, and then you'd break it on purpose just to see how strong it was. It was this slow, super expensive, and you can imagine, often really frustrating cycle.
And you know, that old way, it wasn't just slow. It was a massive roadblock to any real innovation. I mean, think about it. If you have to physically build every single one of your ideas just to see if it works, you're not just limited by time and money. You're limited by what you can even imagine making in the first place. Progress was crawling, not leaping. We really needed a better way.
In that better way, it's called multi-scale simulation. And listen, this isn't just about doing the old thing faster. It's a complete game changer, a total paradigm shift. It lets scientists stop, accidentally discovering materials and start designing them with incredible precision. They can build and test everything inside a computer before a single real-world atom is ever touched.
So what is it like? Well, think of it like having a set of infinitely powerful digital microscopes. You can start with the full-sized part, our turbine blade, and just zoom all the way in, right down to seeing how individual atoms are interacting with each other. You can see how a material behaves at every single level, from what you can hold in your hand right down to the quantum realm. It's incredible. Okay, so what are we actually looking at with these digital microscopes? Let's break down the different scales that material scientists work with, because this is how they build up their understanding from the ground up.
Right, so first you start with the big picture, the macro scale. That's the whole component. Then you zoom into the micro scale. This is where you can see the crystal structure of the material, what scientists call its grains. And then you go even deeper, all the way to the nanoscale. And this is where the magic happens, because the way individual atoms are arranged here, well, that determines pretty much everything.
Okay, so here's the cool part. Each of these scales has its own specialized digital tool. For the big stuff, the macro level, you've got something called finite element modeling. For these super tiny electron structures, you have density functional theory. But for our story today, we're going to hang out right in that sweet spot in the middle, molecular dynamics, or MD for short. This is the tool that simulates how atoms actually move around and interact with each other.
So to simulate all these atoms, a computer can't just wing it, right? It needs a really precise set of instructions. It needs a rule book, basically, that tells it exactly how different atoms are supposed to attract each other, repel each other, and bond together. And in this world, that rule book is called an atomic potential.
And this is absolutely the most crucial point. Choosing the right potential is everything. It's basically the physics engine for your tiny atomic world. You have to match the rulebook to the specific material you're studying and the problem you're trying to solve. If you get it wrong, your simulation isn't science, it's just a bunch of pretty but meaningless digital fiction. So first up in the toolbox, we've got something called the Embedded Atom Method, or EAM. This one is pretty much perfect for modeling metals and alloys, where electrons kind of form this shared sea around all the atoms. It is the perfect rulebook for our nickel-based superalloy. But what if the atoms you're looking at are a bit more particular? They don't share electrons so freely. For materials like ceramics, the actual angle of the bond between atoms is super important. For that, you need a more specific rulebook, like the modified EAM, which takes that directionality into account.
And there's another great option for these directional bonds, called the Tursoff potential. This one, instead of just looking at the angle, it focuses more on the order of the bonds. It does these complex calculations about attractive and repulsive forces between neighbors to figure out how they should all be arranged.
Okay, but what if things get really dynamic? What if you need to simulate an actual chemical reaction, like rust or corrosion, where chemical bonds are literally breaking apart and new ones are forming? For that, you need the big gun, REACS-FF. It's a reactive potential designed specifically to handle the constant making and breaking of bonds. It's the ultimate tool for watching chemistry happen in real time.
All right, so now we're armed with this amazing digital toolbox full of different atomic rulebooks. Let's go back to where we started, to that failed turbine blade, and see if we can crack the case like computational detectives.
So, the official investigation reveals the culprit, and it's a mouthful: corrosive fatigue. And this is basically a 1-2 punch. The material didn't just break from stress over and over. That's the fatigue part. It was also being weakened by a chemical attack right at the atomic level, and that's the corrosion part. A real nasty combination.
So here's exactly how a materials scientist would tackle this. First, they fire up the EAM rulebook to digitally build a perfect replica of that superalloy, atom by atom. Then, once they have their model, they switch over to the REACS-FF rulebook to simulate that corrosive attack. They literally watch the chemistry weaken the structure. And finally, they zoom back out to the macro scale and run a digital stress test on their now damaged model to see exactly where and why it breaks.
And bingo, there it is. The simulation shows them the fatal flaw, the microscopic smoking gun. What's happening is that these unwanted little compounds, they're called precipitates, are forming in these continuous lines right along the material's internal boundaries. You can think of them like tiny, perfect perforations. They create these weak spots where stress builds up until, snap, catastrophic failure. And this right here is the really big takeaway. This isn't just about fixing one broken part. This is about a massive shift from being reactive to being creative. Instead of just finding flaws after the fact, we can now design materials from the atom up. We can write the perfect recipe for a material before it even exists, designing out these flaws from the very beginning. We're not limited anymore by what we can mix in a bucket. We're only limited by the laws of physics and our own creativity. And you know, this amazing technology isn't just for jet engines. This is the key to designing the next generation of batteries, creating more effective and personalized medicines, and building technologies we probably haven't even dreamed of yet. We finally have the tools to build our world, quite literally, one atom at a time. The possibilities, well, they're atomic.